Hello everybody, and welcome to today's chem lesson. Last time we spoke about the individual gas laws made by Boyle, Charles, and Gay-Lussac. Today what we're going to do is look at how those three individual gas laws can be combined into one mega ultimate gas law. Right, we're not going to call it the mega ultimate gas law, which would be better than what we call it, which is the combined gas law. First, right, let's look at each individual formula. Right, we had Boyle's law, which talks about pressure and volume being related. We had Charles' law, which talks about volume and temperature being related. And then we had Gay-Lussac's law, which talks about pressure and temperature being related. Right? If you look at each of these individual gas laws, you might see ways that we could connect them together. When the three of these gas laws get put together, we end up with the combined gas law. And the nice thing about the combined gas law is that it keeps the properties of all the other ones. Alright, we still have P1V1 equals P2V2. Right, so Boyle's law is there and accounted for. We still get volume over temperature equals volume over temperature. So Charles's law is accounted for. And we still have pressure over temperature equals pressure over temperature. So Gay-Lussac's law is accounted for. The combined gas law takes each of the three individual gas laws and combines them together, which is why, again, we call it the combined gas law. Right? It's a pretty straightforward name for what we've done here. And there are two really nice things about the combined gas law. The first one is that, like every other formula we're going to look at, this is located on table T, so that you can always look at the reference table and pull up this exact formula. You don't need to memorize it. It's there for you. The second really nice thing about this gas law is that we can use each of the three individual ones together. If anything in a question or a problem is left constant or unchanged, you can just remove that factor from the equation. Right? For example, if I have a question where temperature is constant, I just take temperature out and I'm left with P1V1 equals P2V2. If I have a question where volume is unchanged, I can just take volume out and I'm left with P1 over T1 equals P2 over T2. We're going to take some time to do a couple of practice problems with this combined gas law. Starting with this one. I have an unknown volume of gas held at a temperature of 115 Kelvin in a container with a pressure of 60 atmospheres. If by increasing the temperature to 225 Kelvin and decreasing the pressure to 30 atmospheres causes the volume of the gas to be 25 liters, how many liters of gas did I start with? And there's a lot of words in that problem, but we can take our equation and we can look at this and apply what we know. We've got a temperature value, right? This is before a change. We have a pressure value before a change. And then we increase the temperature, so we have a second temperature value. We decrease the pressure, so we have a second pressure value. We change the volume, which means we have a second volume. And they're asking how many liters of gas did you start with? All right, we've identified 5 of our 6 variables. Now when we go and we plug into our equation, we have 60 atmospheres. We have a V1 that we're going to search for. We have 115 Kelvin. And on the other side, we have our T2, V2, P2, right? We're going to plug those in their appropriate spots. 30 atmospheres, 25 liters, and 225 Kelvin. When we want to solve this out, we need to do a little bit of algebra. We're going to cross multiply. So we're going to have 60 ATM, V1, 225 Kelvin equals 30 ATM, 25 liters, and 115 Kelvin, right? Cross multiplying our fraction to help solve it. To get V1 by itself, we're going to divide both sides by these two variables, 60 ATM, 225 Kelvin. Which is going to cancel them out from this side. And it's going to leave us that this fraction is equal to V1. And when that fraction gets solved out, we get 6.389. And when I want to know what unit to leave, I have to double check my units in my fraction here. Atmospheres are both on top and bottom, so they are going to cancel out. Kelvin are on both top and bottom, so they are going to cancel out. Meaning the only unit that I have left is liters. Which makes sense because we're talking about a volume measurement. So with careful identification of our variables, careful plugging in and solving, we get our answer of 6.389. As far as gas law problems go, that one's fairly straightforward. Right? They gave us 5 numbers, and there's only 6 variables, so they gave us 5 pieces to solve for 6. What if they're a little bit trickier? Right? Let's look at this problem. A gas at STP has its pressure doubled and its temperature tripled. If the starting volume was 4 liters, what is the new volume? Here, we still have our equation. We still have P1V1 over T1 equals P2V2 over T2. And we can still use that to solve, but there's only one number in this problem. 4 liters is my only number in my starting volume, so that's going to be V1. They're asking us to solve what is the new volume. They're asking us to solve for V2, but I'm still missing any information about pressure, and I'm missing any information about temperature. And so to solve this, you actually need to remember something that we talked about in our previous video. You need to remember that STP is more than just an abbreviation. STP is something that connects directly back to values. Right? That's standard temperature and pressure. And it's on the reference table, it's on table A. And on table A, they tell you that standard temperature is 273 Kelvin, and standard pressure is 1 atmosphere. So STP gives us our P1 value, and our T1 value. We can plug in 1 atmosphere, 4 liters, 273 Kelvin. We're looking for V2. Our pressure was doubled. So if I started with 1, I'm going to have 2 atmospheres. Our temperature was tripled. So if I started with 273, that's going to give me 819 Kelvin. And now all I need to do is solve. I need to do my cross multiplication. 1 ATM, 4 liter, 819 Kelvin equals 273 Kelvin. 2 ATM V2. I need to get V2 by itself, so I'm going to divide both sides by 273 Kelvin and 2 ATM. That's going to mean that this whole fraction is equal to V2, which is equal to, when we solve it out correctly, 5.99 liters. Again, we know it's liters because it's the only unit that doesn't cancel out. Atmospheres are on top and on the bottom. Kelvin are on top and on the bottom, so they cancel out. Liters is the only one that's left. So even though this question only gave us one real number, they told us STP, which connects us back to table A to give us 1 atmosphere and 273 Kelvin. Right? They connected us back to table A to find the rest of what we needed. And then they told us pressure doubled, temperature tripled. So we were able to fill in our P2 and T2 values. Let's try one more. A sample of hydrogen gas has a volume of 3.75 liters at 35 degrees Celsius and 0.89 ATM. If the sample goes to STP, what does the volume become? So here again, they try to trick you. Right? STP is a set of values. We're going to use that for P2 and T2, right? Because it's our after. They gave us a volume, a temperature, and a pressure. So we can plug right in to our equation. Right? We have a P1, 0.89. We have a V1, 3.75. We have a T1, 35 degrees Celsius. We're not going to get fooled by them telling us STP. We know that that means that we need to check table A on the reference table for the values, right? So that's 1 atmosphere and 0 degrees Celsius, and we're solving for V2, and we're feeling really confident, and then we go to try to solve. And we run into a problem. And that problem is this 0. Can't divide by 0. When we multiply this out, we're going to end up with 0. Right? V2 equals 0 liters. And that's because we forgot something that, again, we mentioned in a previous video. When you plug in temperature values into a gas law equation, they must be in Kelvin. So 35 Celsius, that's a fine temperature. That's great. We love it. But It does not fit into this problem. We need to replace it with its Kelvin equivalent, which is 308 Kelvin. 0 degrees Celsius, totally fine temperature, love it, but it does not fit into this equation. We need to replace it with its Kelvin equivalent, 273 Kelvin. And now we can appropriately solve. When we cross multiply, right, 0.89 atmospheres, 3.75 liters, 273 Kelvin. It's going to be equal to my other side of the cross multiplication, 308 Kelvin times 1 atmosphere times V2. We got to get V2 by itself, so we're going to divide both sides, 308 Kelvin and 1 atmosphere. So we get our cancellation here. 308 Kelvin and 1 atmosphere. And when we solve for V2, we are going to end up with a number that looks like this. 2.958 liters is going to be equal to V2. Right? Again, liters is the only unit that doesn't cancel out. You have atmospheres on top and bottom, so they cancel. Kelvin on top and bottom, so they cancel, leaving liters as the only unit that fits. So there are two important things to always remember when you're doing a gas law problem. The first thing is that STP correlates to actual values that you can find on the reference table and plug in for pressure and temperature. And the second thing is that temperature values, even though we love Celsius and Celsius is fantastic, we cannot use degrees Celsius as our temperature values for gas laws. Right? We must use Kelvin, so it must convert to Kelvin before we solve. As far as rounding, right, there's a question in the chat about rounding. It doesn't matter where you round to. You could have written 2.96 liters, and that would have also been totally fine. And with that, I'm going to ask to transition to the Google Classroom, our Google Meet, where we're going to take attendance and do some more practice problems. And I will see you all there.